Water. Water really is unusual. We take it for granted because we deal with it all the time. We drink it, we bathe in it, we swim in it, we throw it at each other. It's the most common and the most important liquid on Earth. There are not very many substances that we are familiar with in the liquid state. Can you think of another pure substance that's a liquid? Mercury. Do we deal with mercury very much? Is it real useful? It's useful for certain applications. Things like gasoline. Gasoline is a mixture, but gasoline is a liquid. Most of the things that are liquids that we deal with, like my Diet Dr. Pepper, the liquid in there is water. And there's stuff dissolved in the water that makes it more fun to drink than plain water. A lot of the things you have in your refrigerator that are liquids, milk. What's the main liquid in milk? Water. It's got some other stuff dissolved in it. But water is by far the most common liquid on Earth. And you think about the oceans and the lakes. Those are all water. It's essential for life. In fact, one of the things that they're looking for when they go looking for life on other planets is there water. It has a low molar mass, but it's a liquid at room temperature. And that's unusual. We looked at that when we talked about intermolecular forces, and that's because of the hydrogen bonding. Usually things with lower molar masses have lower melting points because the intermolecular forces are not as strong. But because water has hydrogen bonding, it remains a liquid at room temperature. It's the main solvent in living organisms and in the environment. It has an unusually high specific heat capacity. And that's what moderates climate. It takes a lot of energy to change the temperature of water, much more than other things. And likewise, it can give off a lot of heat before it changes temperature. Another weird thing about water is it expands upon freezing. Most things, as they freeze, compress slightly. They become slightly more dense, but water becomes less dense. Here is a graph of boiling point of substance as a function of period in the periodic table. So period 2, these are hydrogen compounds with the period 2 elements. There's oxygen, fluorine, nitrogen, and carbon. The period 3, period 4, period 5 elements. And we see trends here. So in, there's no periodic table over there. It's behind me. In group 4A, that's the orange line, carbon, silicon, germanium, tin form compounds with hydrogen, and there is a definite trend within their boiling points. As you go to larger central atoms, the boiling point increases. These are all nonpolar molecules, and what kind of intermolecular forces do they have? Dispersion forces. Dispersion forces are dependent on size. The larger the atom or molecule, the stronger the dispersion forces, partly because the electrons are more polarizable, it's easier to get an induced dipole, and partly because there's greater surface area for them to be stuck to each other. So the yellow one is the group 5A. I should know these, I'm blanking. And for group 5A, we see a trend for phosphorus, arsenic, and antimony, but nitrogen has an unexpectedly high boiling point. Well, why is ammonia's boiling point higher than what we would predict? Hydrogen bonding. Because we would predict that this would go down something like that, right? But it doesn't, it goes up. ET phone home. Here we've got hydrogen and nitrogen. We've got the ingredients for hydrogen bonding. And for the green ones are the halogens. The trend, we might expect that hydrogen fluoride would boil around there. But again, hydrogen fluoride, fluorine is one of those elements that can engage in hydrogen bonding. And then the biggest deviation from expected is for water. We expect the boiling point of water to be down here somewhere, probably closer to minus 100 degrees, and yet it's way up here. And that's because of the hydrogen bonding that occurs within the water. So all these other substances are solids. No, sorry. Never mind. Scratch that. I don't know where I was going, but I got lost on the way, and I don't think it was a great place to go anyway. Water pollution. So this is one of the touchy-feely parts of your book. That's what I call them anyway. So a lot of them I choose not to talk about, but this one I think is better. So water quality is important, right? We need clean water to live. There are different kinds of contaminants, and I think it's good for people to know the different kinds. So there are biological contaminants. These are microorganisms that cause diseases, cholera, dysentery, hepatitis. These are diseases that are hard to treat and can kill people. And they're caused by microorganisms. So you have biological living things in the water. And these commonly get into the water from animal or human waste. They can also get onto fruit, vegetables. You know, you hear about people getting E. coli from lettuce or strawberries, and that usually is associated with cows nearby, and you know, they do what cows do and make cow pies, and then it rains and the water runs over the cow pies and into the stream, which gets used to water the strawberries. And so you get these microorganisms from the cow poop, the manure, getting onto the fruit. So you can treat biological contaminants either chemically with an agent to kill the organisms, chlorine can do that, or by boiling the water, and you can get rid of it that way. So biological contaminants are relatively easy to treat. There are also chemical contaminants, and these are pesticide residues, fertilizer residues, things that you use in your house to clean, or solvents. They're chemicals. They're not alive. They can't be killed. And so boiling does nothing to get rid of chemical contaminants. So, you know, if you've got dioxin in your water, boiling it is not going to get rid of it. If you have a volatile contaminant, then boiling will probably get it out. But many of these are non-volatile, and so boiling doesn't do any good at all.